inspiration for adopting Industry 4.0 practices in academia and industry. Thank you for being a part of this initiative, and I wish you all a productive and enriching experience. Thank you.
Thank you, sir, for your insightful and thought-provoking address. So, before we move on, let me express my gratitude to Professor Vishwesh Badika, sir, one of the coordinators of this faculty development program and Dean of Academic Affairs at Pandit Deendayal Energy University, for his immense support in making this event a success. Sir has an impressive academic background, including a PhD in metallurgical engineering and a diploma in international welding engineering. He has dedicated over 17 years to teaching and research, specializing in advanced welding processes. With research funding from agencies like ISRO, DRDO, and DST, he has completed numerous research and development projects and guided over 50 MTech and PhD students. Sir has also authored 100 plus journal papers, book chapters, and conference papers. His contributions to the field of welding have earned him prestigious awards and recognition. Now, I would like to invite Professor Vishwesh Badika sir to summarize about this FDP and deliver the vote of thanks. Sir.
Yeah, thank you, Dr. Manoj. Can you please confirm whether the slide is visible?
Yes, yes, it is visible, sir.
Okay, okay, fine. So good evening, everyone, and welcome to this 1 week faculty development program. So this program is, as you know, it is funded by AICT, and it has been jointly organized by both the department and the professional body called Indian Institute of Welding. So I take around 3 to 5 minutes to give you some of the glimpse in this short presentation. So PDPU has a very specific role to play as far as national development is concerned. So PDPU is mainly for training the energy soldiers for the nations. As I mentioned, as our honorable director sir also mentioned, we are from the School of Technology, and under the university there are 4 different schools are there: School of Technology, School of Liberal Studies, School of Management, and School of Energy Technology. And Department of Mechanical Engineering and Department of Mathematics, we fall under the School of Technology. And the whole intention of the university is to make the energy soldiers for the nation. So with this, the university was established in the year 2007. So moving further into this, our today's, this 6 day faculty development program is on Industry 4.0 for smart manufacturing. So we are all familiar with there are different versions of, different way of revolutions of industry, where in Industry 1.0, 2.0, 3.0, and 4.0. The current era is Industry 4.0, wherein the today's, this 1 week faculty development program is focused on. So these are the sub areas, or you can say these are the all 9 verticals of Industry 4.0, which will be discussed during this 6 day faculty development program, starting from, you can say, the big data, the advanced robotics, the simulations, the integration, the Internet of Things, AI, cybersecurity, additive manufacturing, and all those things. Here, I would like to mention for the benefit of the faculty, those who are attending this particular program. In this university, PDU, wherein the curriculum 2024 has been recently formed. And in this curriculum, the Industry 4.0 is a regular course for all engineering students. Whether you are a civil engineering student or a computer science student, you are required to undergo the Industry 4.0 course. In addition to that, this year, another important course which has been made compulsory to all engineering students, it is artificial intelligence. AI is another important course which has been made compulsory to all engineering students. So with the advancement in the industries, we also need to review and refine the syllabus. So this is another development. And moving further into that, these are the few important initiatives of our university, which is mainly in the area of manufacturing skill set. University is spearheading the manufacturing skills in the area of solar energy, metal printer, the wind energy, geothermal, the energy storage, oil and gas industry. And that too, there are some more important skills like semiconductors, biofuel, offshore, CO2, hydrogen, smart energy. Those things are there. So these are some of the initiatives of the university. which university is actively pursuing all this skill set. And not only just for the research, but these things are very much in sync with the regular curriculum also. So if you look at the PDPU is aligned its vision with the national initiatives like Make in India, Make for the World, Digital India, Swachh Bharat Abhiyan, Startup India, Skill India. So these are some of the initiatives of Government of India, and PDPU is already aligned with these initiatives. And the most important feature of our university is that under the innovation, which is under the innovation category in the NIRF ranking, university has been featured in the top 50 category. This is a very, very important thing under the innovation category. So at the same time, the university has many infrastructure available. I'll scroll through these slides, and especially many faculty members are attending this program. So we have the 3D printing lab for initial skill development. We also have a dedicated metal 3D printing facility, as our director sir mentioned in his speech. So this is metal 3D printing facility available on our campus. And in addition to that, we conduct a lot of training programs for our trainers also, as well as for our students also. Train the Trainer is another important program that we do conduct for our faculty laboratory staff member also. These are some of the statistics which can help you to understand the kind of the training that we have conducted in Metal 3D in last 1 year. Close to 300 students we have trained. Now, why IIW has into the picture? Because IIW and PDPU has signed formal MOU for the development of welding science and technology. So this was a formal MOU which was signed between IIW and PDPU the last year in the month of August. And that's how we are conducting this program in collaboration with the professional body, IIW, and wherein we have some speakers also from IIW. So this was the MOU. And with this MOU, idea is this IIW India will help us to strengthen the research in infrastructure, especially in the area of metal joining. And these are some of the areas in which we are working currently. And these are some of the pictures probably may help you to understand the kind of the infrastructure that we have in the area of welding research. And so this is the latest addition in our welding research center called Laser Welding Cutting and Cleaning Facility. And we do have a lot of characterization facility in our lab. I mean, we have a pin-on-disc facility. We do have a dry and slurry abrasion tester. We have a high temperature tensile testing also. And there are some other automatic polishing unit and metallurgical microscope as well. So this facility has been shared with many students of many other universities for their MTech, PhD, and the skill development and joint publications also. And this facility has been developed through the funding from various funding from the central government and the state government and the university funding. And these are like projects which we got from central government and the state government and in-house funding as well for the development of the research. Now, these are the few glimpses wherein senior officials from American Welding Society visited and interacted with our director and the director general for the expansion of this welding research center. So these are some of the glimpses for that particular visit. And so this is, and in addition to that, we also have IIW PDU students chapter here. We do conduct a lot of activity for the benefits of the students. So probably we'll discuss more about this particular activity in subsequent session. So I would like to thank Dr. Manoj for giving me the wonderful opportunity to share this short presentation. And so with this, I thank the organizer, and I think with this, I'm done, Dr. Manoj. We can go ahead with our next speaker. Thank you.
Thank you, sir, for giving the brief description about what that is going on in PDEU in the departments as well as in the school. So thank you once again. So before moving ahead, I would like to request all the participants, all the delegates who are actually attending this week faculty development program to please switch on their video so that we can click some photographs. Dharmik, are you clicking it?
Yes, sir.
बताओ, मुझे लगता है स्कूल के
Okay.
होंगे।
Done. Okay. Thank you. We are actually done with the inauguration. So we are moving ahead with the session, but I request you all to give 5 minutes break so that our next speaker can join.
बस चल रहा है बढ़िया। एलजे, हाँ, सरखेज, एलजे कॉलेज ऑफ इंजीनियरिंग।
Very good evening once again. Now moving ahead, I would now like to invite Mr. Chintan Moresia, Assistant Professor from LJ Institute of Engineering and Technology, to introduce our next speaker, Dr. Neerav from Institute for Plasma Research, Ahmedabad. So over to you, Chintan sir.
Yes. Good evening, everyone. I'm audible to you all.
Yes, you are audible. Please.
Yeah. Thank you so much, sir. It is an honor to be here today among esteemed professionals and curious minds eager to learn and exchange ideas. I look forward to contributing meaningfully to our collective knowledge and fostering fruitful discussions. I warmly welcome you all to this enlightening session of our Expert Talk series. It is my pleasure to introduce Dr. Nirav Jamnapura, a metallurgist with over 2 decades of experience in the field of surface engineering and coatings, with a focus on plasma technology applications. His expertise spans research and development in metallurgical coatings, surface engineering, materials characterization, and technology management. Dr. Jamnapura is deeply involved in developing next generation energy materials designed to withstand extreme conditions, particularly in power systems and components. His technical specialization includes high temperature corrosion, plasma technology applications, and intellectual property management, among others. He has been recognized with the Young Researcher Award by SSPC India in 2015 and honored as a Fellow of ASM International USA in 2023. Dr. Jamnapura will be speaking on the topic plasma processing as a tool for green manufacturing. We are excited to hear his insights on this important subject. Please join me in welcoming Dr. Nirav Jamnapura. So please, sir, now please give detailed insight on this exciting topic. Yes, please, sir.
Uh, Thank you, Professor Chintan. Am I audible?
Yes,
Yes, sir.
Okay. Thank you. Thank you very much, Professor Chintan. Thank you, Dr. Vishwesh Badeka, Professor Manoj Seni, and all the organizers for conducting this wonderful program. And I am sure this would be a valuable program for every one of us to know various areas of growth and novel developments. Uh, my topic for today is related to green manufacturing, and I just sharing my slide. Just hold on, please. Is this visible?
Yes, sir.
Yes, sir. It is visible.
Yeah. So my topic is plasma as a tool for green manufacturing, and as we all know, there is a dire need for a green economy. We all are experiences a lot of change in the ongoing environmental changes with unprecedented rainfall. Somewhere it is drought, and with a lot of temperature changes as well. And as we can see in this chart, it is directly linked with the population growth over the years. As the human population exponentially grows, we are continuously emitting carbon dioxide, not just ourselves, but we are using a lot of synthetic materials, which also contribute to the generation of carbon dioxide. And therefore, an increase in carbon dioxide is significantly going to hamper the environment, as we all very well know. So the two major factors are exponential increase in population, which is directly linked with the increase in the synthetic materials, as well as directly linked with the consumption of energy. So more the population, more the energy demand, and more the energy demand, more we generate carbon dioxide. So we are going into a loop, which is going to be a serious threat if we are not able to do something over this. So what are the ways in which we could at least curb this uh, in terms of, at least if we are not able to 100% prevent this, how are we going to reduce our footprint? How are we going to reduce the carbon dioxide that we are generating? So basically, as we are all taught, it is 3R: reduce, reuse, and recycle is the approach. So we can reduce the carbon emissions by several approaches. One of the common approaches being implemented on a national scale is the use of renewable energy. Solar energy, wind energy, etc. are highly being promoted. And another alternative is the reduction of carbon emissions by greener technologies. like hydrogen generation. A lot of people have been talking about the hydrogen generation, hydrogen electrolysis technology. Now, suddenly, people have found that splitting of water has been a very green source of uh, hydrogen, but nobody knows whether the economics are going to work well or not, because it calls for fresh water, and we all know fresh water sources in the world are less than 2%, and therefore we have to also focus on how we can use seawater and at the same time remain economically viable. So what are the other alternatives of green technologies? So one is the hydrogen based processing or hydrogen based technologies. Another is carbon capture technology. So when we are generating carbon dioxide, we try to use and recycle the carbon dioxide back to its process, or we try to capture the carbon dioxide in some form, either convert them in solid or dissolve it in some liquid. So there are several carbon capture technologies available in the market, and a lot of them are emerging, promising. But again, these things are purely dependent on how mature these technologies become. And the third is reducing the emissions by greener technologies. For example, using plasma as a processing tool, which reduces the generation of CO2 itself. Like for example, when we use combustion-based thermal energy systems, we combust a lot of fossil fuels, and these can readily be reduced by the use of plasma technology, which does not need any combustion, and these can be readily driven using renewable sources of energy, and therefore can be a viable option. So what is the role of plasma in green? So there are several, I will be talking about several technologies here. One is the role of plasma in hydrogen generation. That is, we are trying to demonstrate waste to wealth technology. Then there is another option is generation of hydrogen from we flare out a lot of natural gas in several overseas and domestic uh, uh, oil drilling stations, like we have Bombay High, right? So continuously natural gas is being flared out. So there are several methane-based gases can be captured, and hydrogen can be extracted out from these methane, and this can then be used, whereas the carbon can be again brought back to system. So this is one of the option. Another is plasma in carbon capture and recycle. That is plasma for catalysis. I'm going to talk about. Third is plasma in manufacturing. We are going to talk about the plasma in heat treatment, nitriding, carburizing, plasma wire annealing, which is a surface treatment, bright annealing treatment, and plasma cupola, which is another new development. It has been quite a long time, but now it has suddenly become more relevant because of the green alternative. So coming little bit about introducing about plasmas. Around 99% of the universe is in plasma state. Only 1% relates to solids, liquids, and gases. So we can understand that the world or the universe is largely comprised of plasma state, which is a very energetic state of matter. So when we give energy to solids, the atoms gain energy and they start moving randomly, therefore becoming liquids. And when we further give energy to liquids, they get converted to gas molecules, which are further apart from each other. And when we further give energy to these gas molecules by way of temperature or by way of electrical energy, it gets to converted to ionized state of matter. When we give energy, the electrons from these molecules get ripped off from their orbitals, and a charged, a mixture of charged particles, neutrals, is created, which is known as plasma. So plasma is nothing but a state of matter comprised of ions, electrons, and neutrons. It's a quasi-neutral medium, And it is very, very reactive in nature because the ions are continuously in the desire to get stabilized, and thereby they react with all the surface states of matter they interact with. So what we do here is try to react the fourth state of matter with the other three states, that is solids, liquids, and gases. The way in which we do these kind of reactions shall be discussed further. Now, about the Institute for Plasma Research, just because my talk is related to plasma technologies, it is necessary that we communicate about the background of our institute. The Institute for Plasma Research is a research institute under the Department of Atomic Energy, and it works on its long-term objective of achieving thermonuclear fusion as a source of energy. And IPR has a roadmap with a three-pronged approach. One is nuclear fusion and allied technologies. The second is societal and industrial applications, so that we can use the know-how on plasma science and technology for society and industry, and thereby support the human development. And the third one is human capital development, because plasma technology calls for specialized expertise related to plasmas, its generation, its processing, and diagnostics. And therefore, skilled workforce is very, very vital to sustain this roadmap. And therefore, human capital is one of the prime areas. So IPR has several campuses. So its main campus is in IPR Bhat, Gandhinagar, very close to Ahmedabad Airport. Another campus is ITER India campus, which is just behind IPR main campus. Another campus is a FCIPT campus, which is around 25 kilometers away in Sector 25 Gandhinagar. And another campus is the Center for Plasma Physics, which is in Guwahati. So with these campuses, IPR tries to address a lot of plasma science and technology related research goals. Now, IPR has several domain areas like tokamak system. Tokamak is a nuclear fusion reactor model, which is magnetically confined system. And we have two set tokamaks, Aditya and SST1. And we have allied fusion technologies expertise, remote handling, and robotics. We have we work on simulation and theory so that we can complement the simulation requirements of the fusion energy. We also work on power supply development, data acquisition and control, LIGO, and we also have mega science project like ITER organization and LIGO. And we have a dedicated center, FCAPT, working on societal and industrial technologies. So, and we additionally, we have established another Atal Incubation Center, which is there to commercialize all the technologies from IPR. So we have been working on several fronts, area sectors to develop technologies relevant to industry and society. So energy sector is one of them, industrial sector, strategic sector, social and health and environment sectors. And as you can see, there are several domain areas on which we have been working. Now coming back to the plasma science, what we do is plasma broadly we can classify into two forms. One is a thermal plasmas, which are very, very high temperature plasmas, where the electron temperature and the average gas temperatures are same, almost the same. On the other hand, non-thermal plasmas are also known as cold plasmas, where the average gas temperature is much, much lower than the electron temperature, which means the cold plasmas can be as cold as room temperatures. We can even touch with our fingers, and it can be as high as 300, 400 degrees. The degree of ionization here in non-thermal plasmas is very, very less than 1%. And in thermal plasma, the degree of ionization is very, very high. So why plasmas? So basically, plasmas possesses very active species like ions, electrons, and neutrals. And therefore, such active species, they accelerate the chemical reactions. A lot of chemical reaction steps are avoided because of this active state of matter. And the thermal plasmas, to be specific, are very good source of heat and high temperature. So therefore, it can also replace a several number of conventional combustion-based technologies. The glow discharge plasma provides homogeneity across its exposure to materials, and therefore is very crucial and beneficial as compared to the line of sight processes. And also plasma covers the contours of the materials and surface, and therefore it is environment friendly because it does not use toxic gases which are hard to dispose of. So there are several applications that we address. One is where low temperature plasmas are used, where the surface is modified and activated for a specific cause. Like we can do wettability, we can improve the wetting properties, make it to hydrophobic or hydrophilic as we need. Then there are surface diffusion techniques, wherein the species from plasma, such as nitrogen, diffuses inside the substrate and forms hard nitrides subsurface region, and therefore these are diffusion coating which are formed beneath the surface of the material substrate. On the other hand, there are overlay coatings where the material is deposited by plasma processing on the surface of the material. That is, the additional material is built up on the surface. That's why it is known as overlay coating. PVD, physical vapor deposition, chemical vapor deposition, etc. A few such examples of the processes involving plasma overlay process coating. These were low temperature plasmas, and therefore they are linked with only surface modification. The fourth kind of plasma we can use is for high temperature plasma, that is thermal plasma. And because of the high heat capacity, these kind of plasmas are used for bulk modification, melting, smelting, nanopowder generation, waste disposal, etc. are the applications in which these type of thermal plasmas are heavily used. So what we do is we explore these kind of plasmas for several different applications: defense, aerospace, textile, environment, agriculture, water, mining and construction, engineering, automobile and energy sector. And so we have seen several different types of plasmas around us, right? Sun is one type of plasma, which it's a fusion reactor already, to which we appreciate, and which is the source of energy for all our daily activities. And another form of plasma around us is lightning that we see. Plasma torches are man-made plasmas. Plasma TV, plasma cutting, neon lights, etc. All of these are man-made plasmas. Plasma aurora in northern lights are the naturally occurring plasma on the northern and southern poles. So these are types of plasmas that we see around us. What we do is somewhat different. So here you can see on the first this thing, you can see a pencil torch, you can see the thumbnail on which the plasma is being directed. So this the purpose of showing this image was to convey that how cold these kind of plasma torches would be. These are safe for humans and can be beneficial in several medical applications as well. Another plasmas are subatmospheric plasmas like RF and glow discharge and magnetron plasmas. And the thermal plasmas, as you can see, are very high temperature plasmas, and the DBD plasmas are those which can be used for roll-to-roll and continuous processing. So coming to plasma for hydrogen. So what we do is, see, basically green hydrogen is India's actions have been taken. The Union Cabinet had approved National Green Hydrogen Mission, and the expected deliverables by 2030 are 60 to 100 gigawatt of electrolyzer capacity. I'd like to ask anybody, can anyone tell why suddenly these electrolyzers have become so much talk of the town? Anyone? Hello? Hello? Am I audible?
Yes, sir.
Sir,
Audible.
for
Audible.
sustainable environment.
No, why electrolysis was known for years together, isn't it?
Produce
So
hydrogen
why
from
suddenly is it? Yeah, but so hydrogen was known, right? We even in the childhood we used to know that when we split, water splitting is done using electrolysis. So why suddenly this has become popular? This should have been popular years back too, right?
because the fossil fuel are limited, and we want to decarbonize the supply chain. That's why.
So fossil fuels were limited even 20 years back. What has changed suddenly?
To achieve the net
Awareness.
zero.
There is a scientific reason. There are no policy reasons for this.
Okay, sir.
So why earlier, anybody knows why earlier this water splitting was not an economically viable option? Because the energy required to split a water molecule H2O was much, much more than what we can get by reuniting the hydrogen and oxygen, right? Hello?
Yes, sir.
Okay, sir.
Yeah. So what happened is the energy required to split water was much, much more than what we were getting. So the efficiency was negative. So that's why it was not economically viable. Now, suddenly what has happened is there have been substantial research work done on
Can you
catalyst,
just repeat this?
catalytic.
Hello.
Yeah,
Can you just repeat once again, sir? I need to understand
yeah.
this.
The energy required to split the water molecule was much, much more than the energy that was generated by uniting the hydrogen and oxygen molecules, atoms, right? So that is the reason it was not popular. It was not being explored. But what happened over the years is a lot of research work was going on to bring this energy down, to bring this energy required to split was being brought down using catalysts, right? So this catalyst brought down the energy to break down these water molecules. So splitting was possible because of catalysts. And these catalysts have played a vital role in paving the road for electrolyzers, right? I'll be talking in plasma electrolysis in further. So I'll be continuing with this green hydrogen. So in 2020, the government of India came up with an ethanol roadmap wherein they had substantially indicated that slowly India will ramp up the ethanol content of the fuel. And today, even we have, I think, reached to 10% or 20% of the ethanol blending is recently implemented. And on a longer run, you can expect up to 50% of ethanol blending in the fuel. Now, in 2022, India's green hydrogen policy was launched, and at the same time, India's electric vehicle policy was also launched, with 30% of vehicles to be converted to EV by 2030. And in 2023, the Green Credit Program was launched by Ministry of Environment and Forest. So basically, a company which goes green is given incentives. So all of these in support with the Swachh Bharat, Atmanirbhar Bharat, and Make in India and Startup India programs corroborated the national goal of green hydrogen. Now, with this government of India's policies, there were certain technologies which came to limelight. I'll be talking to one of the technologies, which is Raudra plasma pyrolysis technology. As we all know, plastics are the problems to all over the world, and we are all facing a lot of menace of the plastics. And the effect of plastic waste on environment and ecology is very well known. Hazardous waste problem of malpractices in disposal is what is witnessed, but government is trying to curb a lot of malpractices. But naturally, these kind of are difficult. Malpractice are difficult to be 100% prevented. So what we do is, for example, epoxy waste from composite industries, hazardous waste from shipbreaking industries, chemical, petrochemical industries, all of these are problematic waste. So what do? Can we not convert this problematic waste into opportunity? So can we not recover hydrogen from these kind of waste? Energy recovery from waste, green disposal. For example, as you can see in the bottommost picture here, these are the filter cartridges of oil refineries. They have very high filtration, this thing, because the feed water chemistry is critical. And these kind of a lot of polymeric polypropylene and other type of cartridges are generated. And these cartridges contain a lot of polluting elements and therefore are categorized under industrial hazardous waste, which are difficult to be disposed. Now, all of these attribute to the waste which are difficult to be disposed, and also they incur costs, and therefore it's a matter of concern. Now, what we can do is, the idea of waste to wealth comes is Government of India is actively considering these options of waste to wealth, and waste as a source of energy is definitely a promise. We can convert fuel, we can generate fuel from waste, we can generate hydrogen from waste, and at the same time, we can also use the carbon credits from waste. That is, when we convert this waste to synthetic fuels, we can convert those carbon credits into revenue form and can be utilized all over the world in carbon economy. And the thermal plasma is one of the promising solutions. As you can see here, the waste is collected and brought to a waste disposal plant conventionally. And then the waste is segregated. It is high temperature pyrolyzed or gasified using thermal plasmas. And it is converted to gases, or it is converted to fuel depending on the use. Or it can be directly converted to electricity. So Raudra plasma gasification technology is one such promise. As you can see in the schematic, so controlled oxygen is given in plasma gasification, which results in exothermic heat. The initial thermal plasma creates an initial temperature ramp up, which is then followed by the controlled oxygen exothermic reactions, which sustain the temperature, and therefore the plasma power can be brought down. Plasma is a regulator of heat source, so therefore can be utilized to maintain the heat required in the primary chamber. And the output can be syngas, which is CO plus H2, and up to 80% of syngas can be produced. And use of syngas for energy production is very well known, and therefore a lot of component of the system is already established, and only a minimum novelty related to plasma processing can be introduced, which can ensure the sustainability of these kind of systems. 80% of the energy from waste can be recovered, and therefore is a big promise. So there is a small model. Like we can say, what we can do is Raudra plasma system is operated. It can convert and utilize plastic waste, and the energy can be wind energy, for example, because wind energy is the very low amount is being paid to wind energy. So wind energy can be used here instead of paying to the grid. The wind energy can be used here for waste disposal, and this makes the plasma processing waste disposal system very competitive and low cost. And after extracting the gases, syngas coming out from the plasma chamber, Raudra system is at 700 to 800 degrees. And with the heat exchanger in place, we can extract the heat and reuse it for energy recovery systems or process heating applications. And the syngas can then be cooled using gas cleaning system. And the gas CO plus H2 can be separated into CO and H2 and can be further utilized. Hydrogen can be stored and used for several processes such as petrochemical plants, iron and steel industry for producing green steels, power production, etc. On the other hand, carbon monoxide can be used to convert CO to fuel conversion process using, for example, LanzaTech is one such process, and synthetic fuel can be generated using this. So there is a small business economics. I'll not go deeper into this, but at least with even if I buy 50 rupees a kg of waste plastic and spend around 25 rupees a kilo in converting it to gas, I would be spending only 75 rupees. On the other hand, I would be generating 575 rupees value worth of synthetic fuels. So therefore, I'll be making a net profit of 500 rupees per kg of plastic, which attributes to around 15 crore per year of surplus. And therefore, this seems to be, of course, there are certain costs which need to be added to this, such as the return on investment, cost of financing, etc. But overall, the system is very, very promising and positive, and I'm sure this can prove to be a vital source of new developments. Coming to carbon capture, what we do is CO2 to fuel. We are trying to work on this. We have the expertise related to non-thermal plasmas. So rising CO2 levels is a problem, but is also an opportunity now. We can treat the carbon dioxide as input feed and convert to synthetic fuels. How can we do that? Now, when we generate, one thing is that we generate CO and H2 by gasification instead of burning, and followed by H2 base synthesis and CO2 synthetic fuel conversion. So plasma catalysis is one of the main steps in which I was just referring a couple of minutes back regarding the catalytic reactions. As we all know, there have been substantial new developments on new catalysts, which help split the water molecules at much lower energy. And therefore, these energies are brought down to such lower levels that reuniting hydrogen and oxygen proves to be a profitable venture, and therefore the plasma electrolysis or electrolysis for hydrogen production has become lately very popular. Now, what we do here is the same catalyst can be used. Yeah, can you repeat? Hello. Yeah,
I think, sir,
okay.
it may be by mistake due to someone.
Yeah, okay. So increasing carbon dioxide, what can be done here is CO2 to CO conversion is possible using plasma catalysis, and this CO can then be converted to synthetic fuels. LanzaTech is one such example, but there are several other processes also. So as you can see here, CO2 is generated, and it is then brought to carbon capture. And carbon capture technique, plasma catalysis is one such technique where we convert the CO2 to carbon monoxide, and this carbon monoxide is then again converted to synthetic fuels such as methanol, ethanol, etc. And this can then be used for bringing back to the system. Now, what does plasma catalysis actually do? What plasma does is plasma brings down the activation energies for reactions, and therefore makes the reaction possible to be executed at a much lower energies, and therefore lower energies, lower temperatures. And further, the catalysts bring this activation energies, bring them further down. What happens is carbon dioxide, CO2 is a difficult molecule to crack, and therefore plasma alone or catalyst alone cannot bring the energy down to such a level that the CO2 splitting becomes an economic process. But plasma and catalyst combined have proved out to be very attractive option. As you can see here, the thermal activation, when you see this barium titanate and HKUST1, these are thermal activation catalysts. Now, the same catalyst, when they were used with plasma, you can see the difference. From 2 and 5.5, it went up to 21.1 to 43% conversion. This is a significant conversion. and cannot be ignored, and it changes the entire game of economics of the entire process, economics and productivity as well. So what happens is, which type of plasma is used here? Plasma type of plasma used here is DBD plasma, which involves a dielectric barrier discharge layer, and there is between these two electrodes, the gas is ionized, and there is a plasma catalyst. There are several configurations where plasma and catalyst are either sequential or they are coexistential, and it can be worked in parallel or in series. And therefore, the reactions, as you can see from this table, which is reported in recently in 2020, there are several applications where CO2 to synthetic fuel via CO is referred. The breakdown of CH4 to hydrogen or synthetic fuel is cited. Air purification, VOC odor in other application. Nitrogen-hydrogen to NH3 for agriculture. NOx synthesis for agri-tech. NOx removal, tar reforming for tar gas to syngas, and plasma water. There are several plasma catalysis applications which can be significantly used. Now here, as you can see here, the targeted products, they have been significantly impacted, and up to 80% conversion has been reported recently. But there are challenges in plasma catalysis. Like for example, there is heterogeneous catalysis reactor models and there are plasma reactor models, and both have their own pros and cons. The engineering challenges are sustaining discharges and high gas flow rates, dependence on pressure, energy of volume of gas is very, very important, and the conversion efficiencies are very, very important. The scalability is another factor which will play a vital role in deciding which process dominates the market. So we have worked, and you can see here the purple glow discharge in the small device here is indicative of the glow discharge plasma that we have developed for exhaust gas treatment, conditioning, for NOx and SOx removal. And the same plasmas are applicable for the same fuels, CO2 to synthetic fuel applications. So plasma assisted manufacturing, plasma nitriding is one such process wherein we use nitrogen and hydrogen mixtures. We don't use ammonia. And so nitrogen-hydrogen mixtures are separate and they can be used to tailor specific surface chemistry and thereby achieving very specific tailored processes, properties which are otherwise not possible to be achieved. Plasma nitriding is possible. Only plasma nitriding is a solution for stainless steels, because stainless steels otherwise have a protective chromium oxide layer on the surface, which acts as a barrier for all other nitriding processes. The plasma bombardment destroys this protective coating and nitrogen diffuses inside to form hard nitrides. So all satellites after INSAT-2E have the plasma nitrided gears, most of them done at IPR and the rest of them done on a system supplied by IPR. So coming to plasma carburizing, so what we are citing here is these are not just lab scale systems, these are actual large scale systems which are being used by industries on a regular basis. And similar is one such new development that we have done is plasma carburizing. Our plasma PSED division headed by Dr. Alfonza and her team, they have developed a diffusion of a process for diffusing carbon at very high temperatures, which results in a carbon-rich surface, which is known as carburizing. This high increased carbon content results in higher surface hardness. It calls for quenching, which results in martensitic transformation on the surface, and higher carbon further adds to the higher hardness. Pack carburizing, liquid carburizing, gas carburizing, and vacuum carburizing are already established processes, and they have their own pros and cons. Plasma carburizing is one such novel process which is very, very eco-friendly and has a very low carbon footprint. Plasma carburizing involves dissociation of hydrocarbon gas in plasma at very high temperatures, 1000 degrees, which results in the diffusion of carbon from gas to the substrates. Quenching can be oil by oil tank, but the high pressure gas quenching is the most recent advance, and today Oil quenching is not considered the gold standard for the heat treatment industry. High pressure gas quenching is what gives tailored results and which is the most desired results preferred by the industry. As you can see here, there's a large scale industrial scale plasma carburizing system, which is based on gas quenching process. And this is recently installed at FCIPT, and we intend to develop the process for different kind of low carbon steels. Now there is a comparison, as you can see in there's a comparison with pack carburizing, liquid carburizing, gas carburizing, vacuum carburizing, and plasma carburizing. The temperatures are more or less the same, ranging from 900 to 1050 or 1100 degrees. The gas temperatures or liquid carburizing temperatures are lower, but the case uniformity is not uniform. The gas consumption is average. Vacuum, of course, the gas consumption is low, but there is definite benefit of vacuum carburizing over other carburizing techniques. And the carburizing time is a few minutes with up to 10 to 20% lower time scales. The investment cost is very high because of high capital equipment. The microstructure is acceptable in the most cases in gas carburizing, and it is optimal in the most cases in case of vacuum carburizing. Plasma carburizing is, of course, the most preferred one with optimized one. The energy spent is lower in vacuum carburizing and plasma carburizing as compared to all others. So because this is a surface hardening technique, we also wanted to compare plasma nitriding and plasma carburizing. To be specific, that plasma nitriding both are interstitial diffusion processes, but nitriding is possible at lower temperatures, whereas plasma carburizing is possible at very, very high temperatures from 950 to 1050 degrees Celsius. And the process several steps are involved, mostly similar, but here in the plasma carburizing, it is high pressure gas quenching with more than 10 bar pressure. The microstructural changes, that is ferrite changes to martensite. In plasma nitriding, there is no change in the microstructure except the nitriding case. The hardening and tempering is required before plasma nitriding, but is not mandatory for plasma carburizing. Process duration is lower in plasma nitriding, and it is lowest in the plasma carburizing because it's just in merely 2 to 4 hours the hardness can be achieved. The case depths are much higher in plasma carburizing, and the applications are specifically plasma carburizing applications are in gears, shafts, bearings, transmission components, etc. Specifically reference to automobile. Coming to another surface treatment technique is plasma wire annealing. As you can see here, what happens is generally wires are drawn by cold working or hot working, and this induces a lot of stresses in the wires. And what happens is these wires then have to be subjected to bright annealing process in bell type hydrogen furnaces, which is another cost addition, and the surface is also not very clean. So plasma wire annealing, what it does is it involves an inline annealing of wire with argon and hydrogen plasmas, and it not only removes the grease, all the oil marks, oil contaminants on the surface, but it also removes the surface oxides. It is 20 times higher, it gives 20 times higher speed and control than conventional tube furnace, and useful for ferrous and non-ferrous, all types of alloys. And these are modular in nature, so you can increase the zone, plasma zone, or the tempering zone as you customize it for the type of wire you need, and can be a very good option. This is a system developed by a Plasmite company of Italy, and it is a very good opportunity for Indian wire industries to adopt this kind of clean technology. The final technology that I'm going to talk about is the plasma cupola. So what happens is conventional cupolas are basically driven by burning of coke, which is high grade metallurgical coke, but it has low control on gas volume and the melt chemistry. And what happens is the plasma torch, when it is used in the 2-year zone, is the bottommost zone just above the tapping point. And this 2-year zone results in accelerated heating of the cupola charge. And it also gives very, very good control of the gas chemistry. So therefore, high temperature instant heating and reaction control are offered by the plasma torch in the cupola. And this plasma cupola gives 50% more production compared to the conventional cupola of the same capacity. It's a time when we now adopt these kind of green technologies. There are several more technologies, but because of the limitation in time, I limit myself here. Thank you very much. Any interest further discussion on these topics, I'm available on pdts@ipr.res.in. Thank you very much. Thank you, everyone.
Yeah, thank you, Dr. Nirav.
Yes. Thank you so much, sir, for this discussion on the topic plasma processing as a tool for green manufacturing. I would like to extend my heartfelt thanks for the same. Sir, with your permission, we would like to start for the Q&A session if possible. Sir, please.
Yes, please.
Yes, so I encourage everyone to participate actively, and if they are having any questions related to this topic, they feel free to ask your questions, whether they are technical or application based. Yes, anyone?
Thank you for the session, sir.
I am Dr. Sandil Kumar.
Hello, sir.
Hello.
Yes, Dr. Sandeep Kumar. Yes, ma'am. I will just give you a chance again also. Yes, sir. Please say.
Okay,
Yes,
sir.
please.
Sir, I have one small doubt. Nowadays, the Elon Musk is using same type of plasma. What type of plasma Elon Musk using their H2O engine? What is your opinion about that one? Kindly share your view. Thank you. I am Dr. Sandil Kumar from Welltech University, Chennai.
Yeah.
Yeah.
There are several types of plasmas that are used, but I'm not specifically understanding which component are you citing for Elon Musk, because the space has a lot of plasmas. As you can see in the Iron Man, the Iron Man uses a pulsar, that is a thruster in the hands, which is nothing but a plasma thruster. So there are several plasma applications which are in rocket propulsion, in space propulsion, but I'm not sure which one are you asking about. So can you elaborate if possible?
Professor, I'm asking, the Elon Musk created a car using this H2O as a fuel. It's converted into the energy, hydrogen energy. Which type of plasma Elon Musk is using and produced that type of car? That is my question.
Oh, this is a car. Okay, okay.
Yeah.
So I have no idea, because these are proprietary information which are not public domain. But yes, for using water, it is basically a combination of plasma and catalysis. You can have plasma electrolyzer, which generates much higher quantity of hydrogen from water, and this can be used for driving a car. You can have hydrogen storage as a medium in the car, and then can be applicable. I have no idea which technique Mr. Elon Musk has used. So I'm sorry, I do not know about the details, right?
Okay, bro. Thank you. Thank you.
Yeah.
Hello.
Thank you.
I'm Dr. Suresh here, sir.
Yeah.
Hello. Yeah. So
Yeah. Please carry on.
Yeah. When you go by the thickness, it will be more. Okay. It is going to affect the surface finish.
Can you repeat?
If the thickness of the workpiece is more,
goes
on increasing. Suppose thickness will go by higher thickness and all. What about
for
the surface
treatment?
finish?
For what
Suppose
treatment?
if you go by the plasma.
You are referring to plasma nitriding, plasma carbonizing?
Yes, plasma nitriding only.
Okay. Yeah, for thickness, you can consider 1 inch 1 hour as the homogenization time. So for the
Okay.
section thickness, as the thickness is higher, you have to consider homogenization time, and then only you
Okay.
should consider the process time required, right?
Okay. Yeah. Yeah. Sometimes it's not taper will be generating. No, that's what I'm asking.
But this is not a major concern because we are not worried about the bulk temperature. We are not changing the bulk microstructure, and therefore it's not a major concern for us. We are only concerned about the surface temperature.
Okay. Thank you, sir. Thank you.
Yeah, welcome.
Yes, Miss Anjali, I think you are having any question.
Yes, sir. Sir, I would like to ask that what are the advantage of green hydrogen over EV, and what is the future of hydrogen fuel in India, and what challenges can it face in future?
See, green hydrogen is generally used for attributed for hydrogen produced using water. Okay, and water, and that too from renewable energy. So when renewable energy, solar or wind is used to split water molecule and produce hydrogen from water, then it is known as green hydrogen. So there is no carbon involved in this kind of splitting. So these kind of, there are challenges is, as I told you, normal water splitting requires normal clean pure water, that is sweet water. But you have sweet water source is very limited. How much sweet water will you bring, right? Rivers are drying up, the glaciers are drying up, so you only have seawater. So you have to work on seawater to sweet water conversion, and then sweet water to electrolyzer hydrogen generation. So which is going to build up the cost, and the efficiencies are going to bring it down, and again it will become economically challenging for it to be permitted into the market. That is one. Second challenge is how you are going to bring in more economically viable catalysts. This is second. The third thing is, when you generate hydrogen, how are you going to store it? Metal hydrides are conventional metal hydrides technologies are only capable to store up to 7% or 6 to 7% of hydrogen. Now we need to bring this capacity, increase this capacity. Currently, metal hydrides, there are tanks which are only gas tank of hydrogen, are very risky, but there is no other option at the moment. Metal hydride, that is hydrogen being stored in solid form. So hydrogen storage is one of the major challenges that is going to come in the future. And for EV, electric vehicle, basically proton exchange membranes and these kind of PIM based hydrogen generator, solid state fuel, solid state devices, uh, uh, fuel cells, etc., are going to play a vital role for EVs, electric vehicles. Even battery materials, they are going to play a vital role. But again, battery disposal is major issue. So fuel cells are going to be one of the most promising in longer term in future.
Okay, sir. Thank you, sir.
Yes, any other is having any specific question? Okay, any last call? Anyone having any question with the same?
Hello, sir. Hello.
Yes.
Yeah.
Yeah. So, sir, is it possible to make this catalyst and plasma in our university? Get budget?
Yeah, we can work it out. You just drop in an email on ptts@ipr.res.in. We'll try to see what you want and whether that could be arranged for. We'll need to understand what you need and whether it falls in the budget limits or not. Because all it calls for is the capital, which is the most crucial part. Right? We'll try to work it out. Just drop me an email and we'll try to see what best we can do.
Sure, sure.
Sir,
Okay.
sir,
Yes.
sir, cupola is for iron and steel making. What is the purpose of cupola plasma?
Yeah, so basically cupola in plasma in cupola is basically adding and reducing the cost, reducing the carbon footprint, and it is reducing the impact on the environment. So it is a cleaner technology. So plasma, the cupola process smelting is remains the same. Only the heat source is converted from conventional coke combustion to plasma based combustion. Right, so additional
Okay.
almost more than 80% of heat is provided by plasma itself. So the reactions required for this thing are the large amount of species are available for the reactions to occur, for reducing the
Sir,
reaction, reducing the
will it
oxides.
replace the coke? Will it replace the coke?
It not at the moment, not reported so far, but gas-based processes can be thought of, can be worked out in such a way that probably making the carbon available can prove to be vital. So what happens is it's a long column of the cupola, and the coke is arranged at several locations so that the carbon monoxide, which is required to reduce the oxide, iron oxide, is available at several locations. So if we use only say methane type of gases and use plasma, then definitely hydrogen and carbon will be available. But at the same time, how we can reduce it needs to be investigated. So yes, yeah, there is a possibility, because if we use hydrogen based reduction, then there is a possibility to generate green steel.
Okay, thank you, sir.
Yeah, thank you.
Yeah. Okay. So I think thank you to everyone for your active participation in today's Q&A session. I would again like to express my heartfelt gratitude to Dr. Nirav Jamnapara for taking the time to share his expertise and for providing such a comprehensive understanding of plasma processing. Your inputs have not only enlightened us, but more inspired us to think about sustainable solutions in manufacturing and beyond. So thank you again, sir, for this important session and the explanatory talk. Thank you once again, sir. Yeah.
Thank you.
Okay.
Thank you. Thank you
Yes.
very much.
Handing over to again Manoj, sir.
Uh, Thank you, Chintan sir. I would like to extend my heartfelt thanks to Dr. Nirav Jamnapara sir for his insightful lecture on plasma processing and its role in green manufacturing. Thank you, sir, once again for accepting our request.
Thank you. So should I leave now?
Thank you, Dr. Nirav.
Oh, okay,
Yeah,
okay, sir.
thank you. Thank you.
Okay,
Okay,
sure.
bye-bye. Take care.
Take
Sir,
care.
photograph, please.
Yes, please. I request you all to please switch on your cameras.
Kind request for me. There are a lot of question in chat box.
Yes, sir. Done, sir.
Coordinator didn't ask about that one. Kindly ask the question from the chat box. And next session itself.
Okay,
Thank you.
sir, we request you because we have not completely muted all the participants, all the delegates. So, if possible, because there is a question and answer session, so you can directly ask. We will take care of it, what that is being given in the chat in the next one. But I request all of you, you can directly also interact with the speaker.
So each person take 20 to 15 minutes for one question means we can ask chat box means
Okay,
easily
sure,
interact
sure.
with expect we
Sure,
can get
sure,
a
no
lot of
problem.
answer. That's why I'm
No
okay,
problem,
thank you.
sir. Sure. We'll take care from the next one, sir. So we'll be having the next section, just taking a break for 2 to 3 minutes.
Hello, good evening, sir.
Okay, so our next speaker has already joined. So moving ahead, now I would like to invite my colleague, Dr. Brijesh Kumar Jha, sir, an associate professor at Pandit Deen Dayal Energy University, to introduce our next speaker, Dr. Ankush Sharma, sir, from Atira, Ahmedabad. Sir, over to you. Brijesh, sir.
Hello, am I audible, sir?
Yes, you are
Yes,
audible,
yes.
sir. You are audible.
Okay. So, thank you so much, sir, for giving me this opportunity. Good evening, all. I am pleased to introduce Dr. Ankush Sharma, Senior Scientific Officer at the Center of Excellence for Composites at Atira, Ahmedabad. Dr. Sharma earned his PhD in Composite Material from Malvi National Institute of Technology, MNIT Jaipur, and holds an MTech in Mechanical Engineering with a specialization in CAD/CAM from Sardar Vallabhbhai National Institute of Technology, SVNIT Surat. With over 8 years of experience in the development of polymer composites for industrial applications, Dr. Sharma has made significant contribution to the field, publishing more than 30 research articles in national and international journals, as well as conference proceedings. He has authored three book chapters for international publishers and served as an editor of 2 books. Dr. Sharma has also filed 2 patents and successfully transferred a technology to the industry. His remarkable contributions were recognized with the ITSR Foundation's Best Research Award in 2020. Dr. Sharma will be speaking on the topic Industry 4.0 for composite industries. Please join me in welcoming Dr. Ankush Sharma. Welcome you, sir.
Yeah, good evening, sir. Thank you very much. Am I audible, sir?
Yes, you're audible, sir.
Yeah. So, first of all, I would like to congratulate PDEU specifically for organizing such a beautiful faculty development program on the emerging area, which is Industry 4.0. And thank you to invite me to share the thoughts on the specific topic. So from here now, I'll share my screen. Yeah. So I hope now the screen is visible.
Yes, visual, sir.
Yes. Okay. So our today's topic is specifically focusing on Industry 4.0 for the composite industries. So before starting the actual technical things, I just introduce the organization where I'm working. So ATIRA, Ahmedabad Textile Industry Research Association. ATIRA established under the leadership of Dr. Vikram Sarabhai, Kastulal Bhai, and the Shanti Swarup Bhatnagar, who is the first director of CSIR in 1947. ATIRA is an approved body of Ministry of Textile, and we have been declared as a center of excellence for the composites by Ministry of Textiles in 2011. So basically, ATIRA, it has been established like when there was a boom into the textile industry, and in order to be served the textile industry, what we can say, like to compete with the international market and to bring the new technology in India. So Dr. Vikram Sarabhai has thought about that why our Indian mills should not be develop the material quality wise, which is equivalent to the export quality or that can be export to the other countries. So with that objective, that ATIRA has been established, and uh, there are total 8 TRS, Textile Research Association in India, and ATIRA is the first TRA which has been established, and we are also the first TRA who is working in the field of technical textiles. Now, once we are talking about the technical textile, so composite, I can say it is a part of the technical textile which comes under the industrial textile. Why it is a part of the technical textile? So specifically, if I focus on the polymer composite, where we are using the high performance fiber or the synthetic or the natural fiber, which comes under the category of the technical textile. We are working in the different like verticals, majorly for research and development, training and skill development, incubation, and industry integration. So as a research association, we are working on the development of the new material, new product, new processes. Specifically, if I talk about the Center of Excellence for the Composites, where we are focusing on the development of new material for considering all sectors, which include from space, aerospace, defense to the building and construction. We also product the new, we develop the new products as per the specific industry. We also perform other things in order to be improve the processes in terms of, like, say for example, any develop any fabrication processes there where it need to be optimized, it need to be make more cost effective, it need to be make like more, I can say, efficient. So we are also working in order to develop the new processes or in order to be improved into the existing processes. As a research association, we are also having this training and skill development is one of the vertical where we just train the human resource. We provide the trained human resource ready to work into the industries. We also like working on the problem solving things on that, and we also provided our consultancy services to the industry. The third aspect is the incubation, where we support the SMEs, MSMEs, and the startups from their idea generation to the product development to the actual, or I can say the scale up of the production. We are approved body of the Ministry of Textile under this National Technical Textile Mission. We have been incubated 3 startups, those who are working in the field of smart textiles, in the field of like this antenna development for the space application, as well as for the defense application. Also, in this incubation services, we provide our infrastructure to utilize by the industry. So say for example, any industry is there who need to be develop the new material, and as of now they don't have the facility. So whatever the facilities available at ATIRA, if they wanted to be utilized, so they can also utilize for their initial development purpose. The last vertical is the industry integration, where we support industry for like from design, or I can say that from build to print as well as from build to design. So where we just provide the support in the design of the new material, specifically composite, design of the component, development of the prototype, and actual manufacturing, and the as well as the testing of that component. So these are the main focus area where we are working. So this all four focus area is applicable for the composite as well as for the textiles. If I talk about the facility wise, so we have composite processing facilities which include the pultrusion machine. So pultrusion, composite, compression molding, vacuum infusion, robotic reading machine, and then the weaving machine specifically to weave all kind of the technical textiles, which include glass fiber, carbon fiber, Kevlar, polyester, nylon, polypropylene. So all kind of the technical textile can be viewed in the different weaving pattern at ATIRA. If I'll talk about the radial braiding machine, so maybe in the coming slides, I'll show you about the radial braiding machine. So which is one kind of the state-of-the-art facility available at ATIRA with the 276 carrier, where you can braid the sleeve from in the bi-direction as well as in the biaxial as well as the triaxial. Now about this remaining processes, so we'll discuss more in detail in the upcoming slides about the pultrusion machine, compression molding process, vacuum infusion process, and how this industry 4.0 is applicable specifically, or how it will be benefited in the sector of the composites. As far as the testing is concerned, so yeah, we have the testing facility from textile to the technical textiles to the composite, and like as we are the NABL accredited laboratories, so we are providing our services to the PAIN India as well as to some other countries for which we are just testing our samples, especially for the composites. Now, if I'll talk about a composite testing facility, so yeah, we have the full-fledged mechanical testing facility over here. Then electrical testing facility, where specifically dry arc, comparative tracking index, blow wire, and the dielectric system that can be measured over here. Then heat and flame. So heat and flame basically, which is very much important testing facility, or the test that I can say required for the mass transportation. As you know now, under this Make in India mission, the bullet train, or I can say the metro and the Vande Bharat, the component has been developed in India, which comes under the mass transport, and this composite need to be tested as per the RDSO. So we have that facility, and we are also empaneled with the RDSO. So we do the testing for the composite industries who are developing the component for the mass transportation. So as per the European standard, we have that all kind of the facility. So up to this is about the ATIRA and what the facilities we have. Now we just jump to our today's topic on the industry 4.0 for the composites. So before going to the see, these are the two different terminology. Like industry 4.0 is a separate area that is applicable for all kind of the sectors, whether it is a manufacturing sector, whether it is a health and care sectors, whether it is a IT sector. So this industry 4.0 is applicable for all sector. However, the composite is a separate, I can say separate area, and how it can be integrated, how this industry 4.0 is integrating with composite, that we'll discuss. So coming to this new image for the manufacturing. So here, like this picture clearly show that how this industry evolution takes place. So the person is sitting on the beach and then he's just discussing like he has designed a program that allow to run their entire plant from the laptop, and he's sitting somewhere else. The entire plant is running only by his fingers. Okay, so this is the new industry evolution, which is a industry 4.0. Here, if you'll see, so just to understand the old era and today's era, so somewhere in 1900, if you'll see, so there are number of horse carriage and only one automobile were there. In just a decade, like if you talk about in 1910, so you can see the picture is just opposite to it. So in the first picture, you can see there are hundreds of the horse carriage, where in the second picture, this horse carriage has been replaced by the automobiles, and only few number of the horse carriage was able to see in 1910. Similarly, once this industry 4.0 or the digital era has come, so if we'll talk about
नहीं सेशन शेयर की बात कर रहा हूँ.
Not older, then you'll see that yesterday the
मुझे नहीं
internet
पता सर, मुझे
for
तो
the
नहीं आया.
people. So only you can see that you can most of the data that has been generated only by the woman for the human. However, if you see now today's the internet of thing, IoT, that has been replaced, like that has been taken almost, like you can see you can operate the entire home appliances by your mobile phone only. Like you have that application. If you'll see now the Samsung mobile is coming with the smart view things, so you can just by using only your mobile, you can operate entire thing of your house. So this is the internet of thing, that most of the data is generated by or by the things or for the things, right? So this is like how this scenario is changing from I can say the from human working to the digitization. Okay. Similarly, if you see like it is what you can see. So you can tell me what you can see here. What is this? So this is a floor machine, like that has been operated by the human. After that, the things has been changed. So you can see here the first industry evolution, the human interaction, or like you can say it is not human power operated, it is a water operated, and things has changed. Then it is motor operated, single machine. After that, the automation has come. So this is how specifically in all the areas the things are changing, like from human power or animal power to the water power to the motor power or the electricity generated through to the automation. So here with this, we can see that how industry evolution takes place. So somewhere in 18th century, late 18th century, the first industrial revolution has took place, where the power generated machine has been evaluated. So first, so in this thrived somewhere in 1760 or 1780s, the steam engine made it debut during the first industry evolution. Also, the extraction of the coal leads to the massive increase in manufacturing processes. It is during this period the mechanization came into the process. See, so here like the human power to the machine power. That's why the mechanization evolution has took place, particularly in this era. This revolution bring an end to the occurrence of the production process in homes. It also initiated the production process to take place in the factories, where specifically built to like so you can say like the factories, like so from human power to the machine power has come into the picture. So like most of the things which generally took place at the home, the factories has been evaluated, the power generated things has been come into the picture. First weaving machine has also come, during this era. First steam engine has been come into this era. So this evolution is not only increase the rate of productivity, but also brought change in both the social as well as the economic words. That's why it is got the name the revolution. And this evolution initiate the change in the economy from agriculture to the manufacturing economy. So you like how this revolution also affect the economy. Okay, and before this evolution, now you can see like the most of the home was place where they made the textiles. Trader used to provide the pupil with the material what they need. Also, they provide the equipment that is required to do the process. Maybe that human intensive instrument that has been provided during those days. This revolution replaced the agriculture with the mechanization, being the foundation of the social economy. Okay, so here in this particular era, the lots of notable invitation, sorry, lots of I can say invention has took place, like the steam engine, what we discussed, the spinning wheel. Spinning wheel basically to convert from I can say raw uh, uh, fiber to convert into the yarn. So first spinning wheel is also the great invention during this era. So this is all about the first industry evolution. If we'll talk about the second industry evolution, which is in the beginning of the 20th century. So here you can see the second industrial revolution has introduced the assembly line. Okay, somewhere in 1870, electrification drive mass production in the variety of the industry. So this revolution has started to use the electricity. So basically you can say the electricity or has been invented during, or the use of the electricity started in this second era of your industry 4.0. So in this particular area, the company or the factory started to be employing more technology during this evolution, and the mass production is possible. Okay, the first automotive line, you can say that this is called the assembly line, or the things has been evaluated during this era. So particularly you can say gas, oil, electricity, all things has been arrived only during this evolution. The engine with the internal combustion engine, the engine with the internal combustion also generated during this era. Automobile as well as the plane helps to transport the product all over the world in this era. So here, so you can see like how this things like from human effort to the I can say the mechanization converted into the first industry evolution. In the second industry evolution, the electricity, oil, gas, mass transportation has been started. And the third industry evolution, which is in between 1970 to 2000, where the great technologies have been emerged in this era. The process of the production becomes automate without the engagement of the human. So you can see like the development of the first programmer PLC has been developed in this era, like 1969, and also the application electronics has come into the picture. Also the internet has been come during this era. So here it is more like you can say less human intervention possible or happens in this particular era. So this like as the internet has been developed, invented during this era. So this particular industry 3.0 is also called the digital revolution. Okay, now if we talk about the fourth, which is the industry 4.0, which increasing the use of the cyber physical system. In January 2011, the industry 4.0 was initiated as a future project by the German federal. Here, like what the era is ongoing today. So this is all comes under the industry 4.0. It depicts the transition in the way of life and also in the work more complex than the previous revolution, So basically, as the new things has been come into the picture, so it is little bit more complex, and still like we have not evaluated fully, or we are not adopted. The industry is not adopted fully the industry 4.0. Specifically, if I'll talk about the composite industry, where the implication of such technology is very, very complex, because here without human interaction, nothing is possible. Still, there are lots of ongoing projects which is like globally. Certain things are at the R&D level. Some things has been implemented at the large scale production. So some like up to certain level it has been possible, but yeah, still the things need to be developed or adopted by the industry, especially for the industry 4.0. So here in this particular slide, we can see like how the phases of earlier industry revolutions, or now how it changes or switch to the industry 4.0. So as we have seen, like the mechanical production has been invented, railway, steam engines. In the 1870 or the second industrial revolution, the mass production, electricity, assembly line has been invented or established. Somewhere in 1960 to 2010, which is the industry 3.0, computers, semiconductors, computing, personal devices, internet has come into the picture. And now if we talk about the industry 4.0, so here in the industry 2.0, you can see the electric mass production has been come into the picture. In industry 3.0, electronics, IT and automation took place. Industry 4.0, where the robotics has come into the picture. So lots of work now. If you'll see the automobile industry, you can say the 100% automation things are there, where they are using the robots from starting as like assembly to the painting. Okay, so where the industry 4.0 is being adopted by the automotive industry. So now we have seen the industry revolution from industry 1.0 to 4.0, but what actually industry 4.0? So it is related to the advanced sensors, controls, platforms, and the modeling. So industry 4.0 is a framework that enables the delivery of information about the production, manufacturing process across the entire value chain. So you can say when it is needed, where it is needed, and in what form it is needed. So that is industry 4.0. I can tell you a simple example. So say for example, when you will see like right, you can now, if I'll talk about the IT evolution. So earlier only like you are able to be write the emails, okay, and you need to send. Now you can schedule the email when it need to be go. It is least concern, like you have just drafted the mail, you have just scheduled the mail that yeah, it should be sent on so and so time. So it is least concern, like whether you are online, you are offline, was you schedule, it will be automatically sent. Okay, so this is like the good example, when it is needed, where it is needed, and when in form it is needed. You can decide the priority based upon your operation that will be required. Okay, you can program those things, so it should take place on the specific time. So make the data as a key asset, which is the key point of this industry 4.0, and it is all about right data, right people, right time, and the right decisions. So this is, you can say, the complete background of your industry 4.0. So industry 4.0 can be defined as the integration of intelligent digital technology into the manufacturing as well as in the industrial processes. It encompasses a set of technologies that include AI, IoT, big data, robotics, automation. So automation is all about industry 4.0. It allows the smart manufacturing and the creation of the intelligent factories. Okay, so like if I'll take an example of simple IoT, okay, it's now internet on things. So you can, now everybody is having the smartphone. You can operate the machine by using your smartphone only. Like if I'll talk about a simple example from your home application or home appliances. Or if we'll talk about the industry, so say for example, I have oven and I just have this internet on things on my mobile, like I have the only one app which is connected with my this oven PLC system. So I can sit only in my office, I can set the temperature and I can set the time. So for that particular time that oven will be started, my metal will be cured or my metal will be heated and automatically it will be closed. So this is the power of this industry 4.0, how it is being now used or uh, applied into the this industry things. It aims to enhance the productivity, efficiency, and the flexibility while enabling more intelligent decision making and customization in the manufacturing as well as in the supply chain operations. So see, like once you have that implemented the industry 4.0 at your place, workplace, so obviously it is going to be increase the productivity. Why? Because now this industry 4.0 is also, you can say, it is a feedback system based upon your past failure. You can improve your process, you can improve your this material only by having this feedback system. So like it by using the sensor, by using this what you can say, the like the different kind of the this AI, you can see that what are the things has been happened, for what purpose for what reason my material is uh, failing. So you can improve those things. So yeah, obviously it is increasing the productivity. It took less time as you are operating the, like by having the digitization. Yeah, you can operate the machines, you can uh, detect the things, you can detect the failure, you can work to improve the failure. So in that way, you can also increase the efficiency of your workplace. By having the cloud computing, you can increase the flexibility. You can take the decision. The industry 4.0 is also helps to make the decision, right decision. Okay, as we discussed, like uh, say for example, my material is having or like my material is failing due to number of reasons. Okay, by having integration of this all sensor and all these things, I can just see like what are the things has been happened. Okay, and by doing the analysis on those parameters, especially to identify the problem, I can implement those things so that it will also help to like take the decision. Yeah, by changing so and so things, my material quality can be improved or my production rate can be increased. Okay, so this is like all about the industry 4.0. Now if we see what things to be added from to step up from industry 3.0 to industry 4.0. Okay, so in industry 4.0, it is a more intelligent system. It covers big data, web technology, cloud computing, machine learning, internet of things, mobile technologies. All devices are connected to the internet. So this all terminology, like we'll see one by one, like what is the meaning of, like how this big data is helping in the production activity, how this machine learning is implementing specifically in the composite sector, also in the manufacturing sector, internet of thing. One more terminology is there, that is called industry internet on thing. The mobile technology is nothing but like these are the things, like you have the mobile apps by which you can operate the machine, by which you can see your past production activity, by which you can give the feedback, by which you can analyze the things. So this is all about the mobile technology. These are some examples like how this industry 4.0 solutions can be applied in today's manufacturing sector. So obviously, if you see in the first picture, that is thermal imaging of the pump and the motor. So you can see like by implementing those kind of things, this is basically one non-contact type of the things where you can see like how this my pump will be behave under the worst condition, measuring the liquid level. Okay, so now you don't need to be put the things into the tanks, you can directly measure like the different like pressure, temperatures. This is only one example, like measuring the liquid level. However, the pressure vessel now, you can simply, you have the dashboard. By sitting into the cabin only, you can see that what is the pressure, what is the temperature of your pressure vessel. Even though now most of the manufacturing process completely by sitting in the cabin only, you can operate things. You have seen, you might have seen the steel manufacturing industry. You might have seen the fiber manufacturing thing. So I can share you one my experience. So I just visited one this glass fiber manufacturing industry where entire things has been automated. So once the raw material is coming, initially the raw material inspections takes place by only by the sensors. They are checking the quality. After that, they need to be poured into the silos. So again, it is automatically system. So all the things has been put, like the raw material has been put into the conveyor. Then it will be going to the silos. After that, you need to be mix the different chemicals in a proper percentage. So only by sitting in your cabin, like the entire dashboard system is there. So only by just clicking on some keys, you can set the parameter. Yeah, my X material should be 50%, my Y material should be 20%, my Z material should be 30%. So in that way, you can automatically, it will become into the hopper, and all the material will be get mixed, and then it will be directly go into the furnace where you can set the different temperature with the time. Okay, automatically it will be heated. Then from the furnace, once the material will be just converted from solid to the liquid, then it should be gravity free flow, and it is passing through the nozzle. And after passing through the nozzle, the water sprays there where it will be again converted to solid, and then it will be winding process last. So the entire thing now, not a single human intervention is there, only to check the quality, like when the material is coming out from the nozzles. So you have to be check like where it is a continuous flow or discontinuous flow. Only in order to maintain those things, the manpower is required, and all these things can be seen on the computer system. They can analyze, they can see like, yeah, what is my production rate, what is my efficiency, up to what time my furnace should be run. So all these things now, it has been digitized. So it is a good example of the industry 4.0. Then you can see the connect customers with the manufacturing. Nowadays, you can see there are lots of manufacturing process. Even though if I talk about the textile industry, so the machines are there now. Only you need to design, say what kind of t-shirt you will be you need to wear. Only you can design this thing. You can give those command to the machines, and directly the machine will give you the final product, which is the t-shirt. Okay, whatever you have designed. So again, it is a good example of your industry 4.0. Then if we talk about the monitoring system, so now the sensors are there which can give you the image into the different color by having the different temperature codes. So you can see like the good example, that the figure, the compost piles. So it has been given with the different colors, the monitor of the temperature of the compost piles. Then the preventive maintenance and the condition monitoring. So yeah, this is also one thing. So by analyzing the data, it will also help to do the preventive maintenance of your machine. It is also help to do the condition monitor of your machine. So lots of sensor that has been now attached with the machine. So whenever any failure has been occur, so it will give you signals, or like you can set your preventing maintenance time to the machine. It will give you indication. Okay, so in that way, the role of the industry 4.0, or you can say the industry 4.0, is applied in the different sectors. Now, what will be the impact of deploying this industry 4.0? So there might be long-term impact, there might be short-term impact. So if you'll see the near term, which is or the short-term impact on your industry 4.0 is the operational efficiency. It asset your utilization, operational cost reduction, and the worker productivity. New product and services, yeah, with the help of this industry 4.0. So industry 4.0, under the industry 4.0, your simulation, augmented reality, these all are the component of your industry 4.0. So here you can, it is easy to design the new material. It is fast to provide the services as per the customer requirement. You can do the customization fastly. You can show the customer after discussing with your customer, after considering all the parameters that has been given by your customer. Yeah, you can see or you can show your customer that yeah, how your product will be look like. So these all are like this software based services, data monetization, pay per use. Yeah, so these are the short term impact. However, if you talk about the long term impact of your implementation of this or deployment of this industry 4.0 is new connected ecosystem. This platform enable the marketplaces autonomous, so it is also helps to pull the economy. So as your efficiency will be increased, your productivity will be increased. Okay, so you are able to fulfill the customer's requirement quality wise. End-to-end solution you can provide your customer. End-to-end automation is also possible. Resource optimization, waste reduction is also possible. So I can give also I can give you an example in terms of the composite industry. So pultrusion is one of the process, like we'll discuss about more in the pultrusion process. So with this, especially this automation, it helps to reduce the waste because it is one kind of the continuous process. Now, whenever the things are required, so say for example, if my production go wrong, so by the sensor, it will be immediately sense, it will give the signal to the next system, yeah, that your product is not coming properly, so it can be immediately stopped. Okay, then you can do the changes, and after that you can start your production. So these are the things like how it will be helpful for or in order to achieve your long term and short term things. So earlier, like still in India, there are so many sectors where still this industry 4.0 is not implemented fully. But now today, like there are certain reasons. So we can consider nowadays, if you see the EVs or e-cars, so the cost of the battery itself is very high. That's why the cost of your automotive or this e-cars are very high. But if you see, like if you consider this year or if you consider the previous year, so there might be changes into the some cost reduction into the this battery products. However, India is also working on the developing of the new this I can say the more batteries or for the automotive where further the cost can be reduced. So in the same way, earlier the cost of the sensor, cost of the application development, cost of the all integration component which will be required to implement this industry 4.0 was high. But if you see now, the cost of adding the sensor to the equipment has been reduces. Cloud computing capacity to handle the data from a large number of sensors are available. Enterprise softwares evolve to operationalize the data from these network devices, to use the data as a source of information for the decision support. So new day by day, new softwares, new applications have been developed. So like from the previous years to adopt this industry 4.0 by the industry, that was very tough. But now the system has been more flexible, where you can now think to implement this industry 4.0 at your place. Yeah, so we understand like what is industry 4.0, what industry 4.0 can do. Now this particular thing, so there are 9 pillars, 9 technological pillars or technology pillars for the industry 4.0. This innovation bridges the physical and the digital world and make a smart and autonomous system. Business and supply chain already use some of this advanced technology, but the full potential of the industry 4.0 come to the life when they are used together. Okay, so what are these 9 pillars? So basically, see, these are the 9 components on which your this industry 4.0 is depend. Or you can say this by combining all these parameters or by adopting these parameters, no, you can say, yeah, you have implemented this industry 4.0. So what are these 9 pillars? So these are the big data and the AI analytics, horizontal and the vertical integration, cloud computing, augmented reality, Internet of Things, or you can say specifically industrial Internet of Things, additive manufacturing or the 3D printing, you can say, robotics, digital twinnings, and the cybersecurity. So these are the nine pillars or 9 component of industry 4.0. We'll discuss one by one these 9 pillars. So first, if we talk about the big data or analytics. So what is the meaning of this big data? So basically, big data means what? Like you used the number of sensors, okay, in your on your machine. Okay, now this all data has been captured. So a huge data is being available with you. Okay, so if you can see, the utilizing the industrial data and the analytics to optimize the production quality, enhance equipment, manage the reduce energy consumption. It is analytics that is at the core of this transformation, enabling the seamless collection and the evaluation of data from diverse sources such as production equipment, system, organizational resource. So you can say, like, say, for example, you have complete system and you have used the different components, like you have the sensor at your machine, you have some data analoger, which is generally capturing the data. Then you have some system on your testing facility, you have some system at your production facility. So all the data has been captured, and this data will be further utilized for the analysis. Okay, for the analysis, in order to be understand, or in order to be recognized, like how your material or how your process, basic not material, but how your process is behaving, what you can do in order to change the things. There are some core processes to analyze the collect the data. So one is the data management, which is a repeatable process to build the standards for the data quality, data mining, predictive analytics, which is some algorithm that will be used to analyze your collected data. In-memory analytics, which is again the analyze the data from the system to gain the immediate insights. Okay, so here we understand this big data by considering some examples. So maybe you can consider one PCB, like PCB manufacturing facility that can be collected data at the different level of the manufacturing processes. If this PCB or a batch of the PCB is found to be faulty, so their manufacturing data, which has been collected at the different source, can be retrieved and analyze their pattern, like how the process took place. And by analyzing this complete pattern, the process can be involved. Those patterns can be redesigned and re-evaluated to reduce the wastage or to increase the productivity. Say, for example, like I have the different stations. I have station 1, 2, 3, and it is a inline facility. So maybe we can consider, like, we can capture the data from the each station. We can analyze. We can see like how I can increase the productivity, how I can increase the efficiency of my product or the process, or as well as if my some product has been come into the faulty, that batch has come faulty. So by analyzing those kind of the data, I can do my process modifications. So ultimately, it will be reduce your I can say the waste. It will help to increase your productivity. Similarly, the second example, or you can consider, so one company, Infineon Technologies, has a semiconductor manufacturing and has reduced the product failure by correlating single chip data encapsulated in the testing phase at the end of the production process with the process data collected in the wafer status phase in the early process. So you can see like from the early phase to the last phase where actual testing takes place. So by analyzing, by correlating those kind of data, they have reduced the product failure. So in this way, like this Industry 4.0 analytics help the company to quickly identify the pattern and assist them on the discharging the faulty chips early in the production process and improve the product quality. So this is like how this big data plays a role in order to be increase the efficiency or in the reduction of the waste. Now, if I talk about the second component or the second pillar of your Industry 4.0, which is horizontal and the vertical system integration. So the most of the function in this organization, but particularly in these pillars, are not like, say for example, in any of the industry, so the functions are not fully integrated. Okay, so here what you need to do, you need to implement end-to-end visibility from plant to product to the automation. And in today's like present, most of the manufacturing IT systems lack of complete integration due to the organization, due to the customer, due to the suppliers that are closely linked. Okay, which are closely linked. So here in this particular, you can see the horizontal and vertical system integration means what? This is a essential framework for Industry 4.0. Okay, which is horizontal vertical integration system, where it is tightly integrated with the field level on the production floor across to the multiple production facility and across to the entire supply chain. Vertical integration system is all layer of an organization are tied together, and the data flow freely from shop floor to the top floor and the back down again. So basically it is you can see it like the whatever the information is generated from top floor to the shop floor, it is vice versa, it is flowing. So there is no chances of, I can say, any mistake. So in that way, like how this horizontal and the vertical integration system takes place. So you can consider again an example. So this Boost Aerospace, which is a company in the Dassault system. So Dassault system is a company which is in the modeling software development. So they have collaboratively launched a platform that serve a common workspace for the manufacturing design collaboration and is available as a service on the private cloud. It is manage all the tricky tasks of exchanging the product and the production data among the multiple partners. Okay, so like you can consider in that way, say for example, I'm just designing, I'm a company who is the composite manufacturing, and obviously the material design is one of the crucial part of this particular process. Okay, so based upon the customer requirement, if I'm designing something, so from the designing phase to the production phase, each data will be shared, and if any changes takes place, so again it is like the information is available with all the I can say the team player which are related to the project. They can see at any stage, they can suggest at any stage, they can do the modification at any stage, and subsequently this decision will be implemented at the production stage. So in that way, this horizontal and vertical integration system takes place. If we'll talk about the third part, which is the cloud computing. So in very first picture of our discussion that we have seen, which is again a good example of the cloud computing. So cloud is a remote system that can be accessed, provided from anywhere using the internet. There are a lot of cloud services available today, of which notable areas like IaaS, PaaS, SaaS, and communication among each machine themselves between the machines and humans are usually backed by the cloud services. So the good example now is that you can see the Amazon.com. So now we are buying the item from the Amazon, and at each stage you can track your order. It is not one-to-one message, but yeah, once the product will become from like it will be go out from the warehouse to each stage, you can see you can get the information, yeah, at what stage my product is, when it will be get delivered. So every time you can check your own package present location and get query is executed in the real time, which is the power of the cloud computing. Again, the cloud computing, which is again helpful. So like what we have seen in the previous slide. So that is also part of the cloud computing where you are just putting your ideas on a cloud. So say for example, when aerospace company is putting that drawing or that's there's all system, and the aerospace company has just generated a common platform where they can put the things on the cloud, which is accessible from any place. Okay, so there is no required to be meet face to face. You can just share the idea. You can just put the things on the cloud. The next is related. The next pillar is your augmented reality. So augmented reality, I can give you a best example. You all might have seen the Lenskart app, which is a good example of the augmented reality. You can see now you have that app. You can just select your face. You can select your this frame, and you can check how it looks on you. So this is the augmented reality. So augmented reality, specifically in the manufacturing sector, is very much helpful. So in the manufacturing sector, or like especially on the product development, as well as in order to be how the maintenance of your instrument. So many companies have adopted this augmented reality, where they are giving training on through this virtual reality or the augmented reality to their manpower. How can they maintain? How can do the maintenance of their system? So augmented reality is a typically overlay the digital content on the real environment. This is still like so many companies adopted, but still it is a emerging area where need to be fully adopted by the company. So here you can we can see in an example when an equipment worth of the some $1 million needing some form of the maintenance. So before carrying out the job on the actual equipment, a training session can be conducted. Once the technician is confident enough to be impeccable, he can do the same thing with the actual equipment. It is a win-win situation. So like what we have discussed, so like the training has been given virtually, and then after having this all kind of the idea, the technician can do the actual job on the product. So the technician does not get embarrassed messing up with the job. So he can understand, he just understood by this virtual reality, he's able to understand the individual part. So he can do the things or he can perform his job properly. So this is like how this augmented reality or virtual reality is useful for things. Now, the next pillar is industry Internet of Things. So again, like you can see, the manufacturing machines are integrated with the sensors and this network that make be use of embedded computing. Most of the physical things in Industry 4.0, like device, machinery, robots, product, equipment, use of sensors to provide the real-time data about the performance, conditions, and the location. Okay, the technology lets organizations run smoother supply chain, rapid modified, design product, stay on the consumer preferences. You can we can understand these things by the example. So how this industry Internet of Thing is applicable. So consider the factory that has run out of the solder, like this soldering wire. Na? So this is one solder company. So there is no point in the pushing out the page of the printer. So again, this is example of the PCB board industry. So when the PCB board is being manufactured, the soldering is required. So say for example, they have the shortage of the solder wires. So there's no point to the pushing out of page of the printing circuit boards when there is no solder lead available to integrate the component. So instead of the human stopping the process, solder lead holder enabled with the sensor that could prompt the inventory team by more solder in the prior, or it can give the signals to the next station. Yeah, as the no further solder wires are available. So again, it will give the signals to the next solder holder. So it will be stop the operation. Okay. So how it is implemented? So say for example, the one sensor is applicable, is adopted or apply on the machine. So yeah, by sensing these things, whether the solder wire is available or not, it can give the signals to the either to the this your operator. Yeah, this solder is not available. So you can bring in the advance or you can stop the machine. Then next pillar is 3D printing or the additive manufacturing, which is also one kind of the emerging area. Okay, so you can whatever you can think, you can like the slogan, if you can dream it, then you can print it. So this is the power of this 3D printing or the additive manufacturing. Most of the aerospace industries has adopted this kind of things for their prototype development, their small part development, to realize the product how look like, to see how it will be performed in the environment. So that kind of things can be developed using this 3D printing technology. So a company made in space has planned to construct a satellite in space. Okay, so this has a lot of added advantage. So highly dense material can be picked and sent to the space where they can be used to construct the object of bigger volume. Because now the payload is also one of the challenge for the space industry. You can consider like to launch a kg of payload into the space from the earth, it cost near about 15 lakh rupees, which is an approximate cost. So you see, you can understand like by reducing a gram of weight for the space is very much helpful, and which is also the crucial. So this kind of the technology is again helping for such kind of a mission where the small component or like the material with the less space, maximum material can be sent to into the space, and where they can actually build the things. So this is like how this 3D printing or the additive manufacturing is helping to the industry as a part of the industry 4.0. Autonomous robots. So this Tesla Motors Gigafactory is an example, good example of this autonomous. They have autonomous indoor vehicles to transfer the material between the workstations, which has the payload of near about 130 pounds, and can even charge their own battery without the intervention. Okay, so the robots are yeah, you can say, which is also one of the important integral part of this industry 4.0. Now most of like you can see the complete automobile industry, where the complete production process takes place by the robot, which is including from assembly, like from welding to the painting, both everywhere you can see these robots. Even in if I talk about the textile industry, or like we have seen like the braiding machine. So we have the braiding machine, which is again connected with the robotic arm, the KUKA robot. So which generally like helps us to like from holding the main rail to define the path of your movement, so that how the braiding will be takes place. So in that way, it is creating the more flexible system for the component development for us. It is automation. We can define the program, so that once we can define, we have designed the program, we have defined the program, then just by having one single dry run, we assure that yeah, whatever the component will be there, which is a perfect or near shape product for us. So this you can see in the object process, which can be gain information about its environment, adopt and make decision without the need for the human intervention. Autonomous robot transfer the raw material, half finish and the complete good in a easier, faster, and the smarter way. So you can see like it is like whenever you have this repeatable work, so where there are, by using this kind of automation, there are less chances for your without compromising the quality, you can do the mass production also. And they operate based on the complex logic algorithm, meaning they don't require any preset path to carry out their duties. So they can do work for the long time. So this is like how autonomous robot is there. Yeah. Simulation digital twinning. Yeah, this is one of the important component of this industry 4.0 and very much needed for the industry. So the digital twinning means what? It is a virtual simulation of the real world product, machine system, or the process based upon the IoT sensors. A simulation in the present days use the design component that are manufactured. Industry 4.0 is able to simulate a virtual environment for the factory itself with the real-time data and analyze the productivity before changing in the factory that can be made. So basically, see what is happening over here. So what we are just creating a digital version of the actual product, actual process. We are creating the same environment virtually, and we are analyzing the performance of your product process under that environment. So without spending much time, much money, you can implement the things, you can check your system. If any fault is there, you can resolve those kind of the fault in the during the actual production. Okay, so this is the power of the digital twinning. A good example like General Electric GE has created first ever digital wind farm, allowing for the testing of the various turbine configurations to optimize real world wind farm performance. And this data, like whatever the performance they are capturing or they are just configuring, so that can be used to demonstrate the, or that can be used for the actual wind farm in order to increase the efficiency and the performance. So this is like how this virtual or I can say the digital twinning is helpful, which is virtual simulation. So say for example, I can give an example in context of the composite. So like for example, I need to have the strength in a specific direction. So what I'll do before going to be make the actual composite part, I'll design the part. I'll define my layup sequence. After that, I can apply whatever the forces will be applicable in actual condition on that component. I can see in what particular direction I can lay up my fiber so that I can have the more strength in the particular direction, and my composite should work or my component should work into that environment. So this is like how the digital twinning is taking place. And the last pillar of this is your cyber security. As we have seen that the big data, cloud computing, all these things are there. So as it is a digital world, so there might be chances of the loss of your data. Okay, then hacking of your data. That's why it is also one of the important pillar of industry 4.0, which is cybersecurity. So cybersecurity becomes the talk of the town since the dawn of the information technology. So the nightmare of loss of your I can the data hacked. So this is the like main glitches of your this kind of the digital world. So the preventing of such catastrophic failure or the safeguard the data and the performance of your server is sole purpose of the cyber security. And how it is going to be affect like this cyber security is very much important, where now most of the people has also consider this as a part of the cyber security. So here like we can consider again, we can consider a example like how it will be the cyber security affect the small firms. So again we can consider the example of your PCB boards, printed circuit boards. So now in this industry 4.0, more and more components are connected, and one device action is based upon the other device, as we have seen like in the previous example, like the this your shoulder holder, like if it shortage of the shoulder, then it can, by the sensor, it can be give the signals to the next station so that your operation can be stopped automatically. So your one system is connected with the other system, and again the performance of one system or the operation of one system is depend based upon your output of the other system. So it is more operational decisions are decentralized and more security concern is raised. Okay, so how, say for example, if this cyber security will not be there, then there might be chances of to hack your system, to change into the design, or maybe the complete blueprint can be erased. Okay, so in order to be prevent all these nightmares, the cyber security is required. Okay, so that's why the integration of the system with the cloud by itself is an advocate that need for the cyber security, and you have a strong system where you need to be prevent by hacking or by resolve by hacking or by just removing the data from the cloud or from the digital world. That's why the cyber security is one of the crucial thing of your industry 4.0. So why industries in India, specifically I'll talk about the composite industry, they are not able to be adopt this industry 4.0. So before implementing this industry 4.0, you have to be see like how you can implement those system at your place. So there are certain stages you can see. So first, map out your industry for the 4.0 strategy. Create an initial pilot project. No need to be implement in your entire system. First, you just create a pilot project. You can see like how this industry 4.0 is helpful and how it will be work in your organization. Define the capabilities that you need. Become a virtue in the data analytics. Transform into the digital enterprise, and actively plan an ecosystem approach. So these are the steps, 6 steps how you can implement this industry 4 at your place. These are some examples of how the old product is connected with the new technology. So you can see the Philips lighting. So user can control the Philips lighting via their smartphones, turning on and off. You can blink as per the program by using smartphone only. Then you can see the in the healthcare, Medtronics. So Medtronics implemented the digital blood and glucose meter connected wirelessly to a monitoring and display the device, and can alert the patient to train the in the glucose level. Similarly, the smart textile or the e-textile, now the uh, like t-shirts are coming in that way so that they can capture the entire data of a player. So you can see the Ralph Lauren's. They have the polo t-shirt available in 2015, and stream the distance covered, calories burned, movement, intensity, heart rate, all the data can be captured. Okay, so this is like how this integration of the new technology is there in the existing product, and they are more advanced. So like once you have the like you have the t-shirt, so you can capture the entire thing, and based upon that you can recognize the pattern, you can do the analysis, you can do the statistics, and then you can change this as per like in order to be improve the efficiency of the product as well as process. Then Babload. So it is a Babload play pure drive product system. Put sensor and the connectivity in the tennis racket handle, allowing user to track the analyze ball speed, spin, and the impact location to improve their game. So like you can see how this digitization or the integration of the industry 4.0 is helping in order to be increase the efficiency, or in order to be like it is like a feedback system, so you can improve the things based upon the requirement. So these are some examples of product evolution by integration of this industry 4.0. So up to this point, we understood. So like as the topic is Industry 4.0 for the composite industry. So up to this point now we understand about Industry 4.0. Now some slides which are related to the composite. So before understanding the Industry 4.0 for the composite, we need to understand the composites. So basically, composite is what it is, the integration of the two or more than two material which are physically distinct, and in order to be get the aggregate result of these two distinct material, we are making a single component by integration of two, which is called the composite. Composite can be natural or the synthetic. That will be depend upon the material that you are selecting. Some of the examples that already which are naturally available. So we have the flesh in our legs reinforced with the bone, concrete with the steel, as you already seen, like from our child, seen the RCC structures, which is also a composite. The wood. So wood itself is a composite material. If you'll see, so the composite is not a new thing. Yeah, but the use of composite or use of the synthetic fibers in the composite, or you can say the actual use of the FRP composite or actual use of the composite at the product level for the industrial level is comes somewhere in the 19th century. So old mud is a good example of the composite where this straw is mixed with the mud in order to make the house. Glued laminated wood in the Egyptian civilization. So in 19th century, the laminated metals in the forging swords. This is also one example of the or like how this composite being used from the 19th century. Actually, in the 20th century, the fiberglass use of the fiberglass come into the pictures. Most of the component for the structural or the semi-structural component has been made through this FRP composites. Now the recent trend, or recently the people are working on the nano composite, where at least one component is in the form of the nano. There are basically three types, or I can say the four types of the composites. So metal matrix composite, polymer matrix composite, ceramic matrix composite, and the fourth one is the carbon matrix composite. In the metal matrix composite, your matrix or the major component is your metal, and you are adding some filler fiber in the different shapes in order to be achieve the desired property. Likewise, in the ceramic, you are using ceramic as a matrix material and adding some component or particulate into it. Likewise, in the polymer matrix composite, your polymer is acting as a matrix material. The polymer may be the thermoset of thermoplast. And the last one is your carbon matrix composite, where carbon is the matrix. So you might have heard about the carbon-carbon composite or carbon silicon carbide composite. So this comes under the category of this carbon-carbon composites. Now, if I'll talk about the polymer matrix composite, see, at Atira, we are only dealing with this polymer matrix composite, specifically for the thermoset matrix composites. So whatever the examples I'll be considering, so these all are based upon only on the polymer matrix composite. And even though like the coming slides will become, or especially the Industry 4.0, the implementation of the Industry 4.0 in the composite will be focused on the fiber reinforced polymer composite area. So the composite, the polymer matrix composite, again, these are the two types based upon the matrix material. So thermoset and the thermoplast. And on the basis of the reinforcement material, so that can be again classified on the like viscous type, particle type, fiber type, like. So in the FRP composite, we have the different constituent. So one is your matrix material, which is in layman language is called the binder. Then we have the reinforcement material, which is in any form, whether it will be in the particulate form, whether it will be in the viscous form, whether it will be in the long fiber form, whether it will be in the fabric form. Then we have the fillers and the additives. Filler additives are added into the composite in order to be achieve the specific property. The reinforce can become into the different, like here the right side you can see the rovings are there, continuous and bulk. So basically when we have the bundle of number of filaments, which is called the roving, then this roving can be used directly for the production. Then we have the yarn. Again, the number of filament can be bundled together in order to be make the yarn. So you can say if they are directly using is roving. If you are doing certain modification like we are twisting it, then it will become under the category of yarn. The yarn can be utilized to again convert into the fabric. In some of the application we are using the strand mate. So the chopped strand mate is there. So the fiber has been chopped and it is converted into the form of like mate. Then we have the surface wheel, which is again the low GSM randomly oriented fabric. So these are the different form of the reinforcement material. Why why composite material? So there are lots of benefits of this FRP composite. High strength to weight ratio, oriented strength. So oriented strength means what? I discussed. I explained the things. So say for example, you will be required the strength in a specific direction, which is like say for example, I'll be required to be design a component which should be where I will be required the strength in a certain like at 45-degree angle. So I can orient my fiber in such a way that I can get the maximum strength in that 45-degree angle direction. So this is like the beauty of this composite material. You can tailor the material as per the requirement. Design flexibility, lightweight, corrosion resistance, large part size is possible. Dimensional stability. So dimensional stability, especially if I'll talk about the carbon-carbon composite or the carbon composite, you can get the good dimensional stability into it. Low thermal conductivity, even though you can by having the different constituent into the composite, you can design the entire material based upon your requirement, right? So this is these are the advantages of your composite material. You can see some of the examples like the development of the development and use of composite in civil aviation. So by 2010, you can see more than 50% material has been replaced by the composite compared to the conventional material. Okay, but why? Because see, if I'll talk about the metal, so where the metal is having the density of near about 7.8 gram per cc, whereas in the composite, especially in the FRP composite, you can get the density of 1.8. The carbon fiber composite is having the density of near about 1.8. So without compromising the actual performance of your component, you can reduce the weight. Okay. So in that way, like the civil aviation where the weight is again the major concern. So that's why the more than 50% component has been replaced by the composite material. If I'll talk about the fibers, so some of the reinforcement material which are widely used into the composite industries are glass fiber, carbon fibers, aramide fibers, basalt fibers. You might have heard about this aramide or Kevlar fiber, which is specifically for the bulletproof application. Carbon fibers are widely used into the aerospace industry. Glass fibers are in general like for the structural application the people are using. Some other less common fibers, which is I can say the specific application purpose. These kind of the fibers are being used like the metallic fiber, quartz fiber, ceramic fibers. Okay. If I talk about the quartz fiber, which is 100% pure silica, it has a good, I can say, the properties which will be required for the radome and space as well as in the aerospace industry. So for that specific purpose, this quartz fiber is being used. Okay, so based upon the application, again, we can select the what kind of the fibers will be required. So that is a part of the material design. Then in composite, again, this weaving pattern is also affect the end performance of your composite. Okay, now this slide I put specifically for the purpose to explain the role of Industry 4.0 in this composite industry. So there is one I can say the advanced technology AFP, automatic fiber placement. Okay, where the fiber will be placed with the help of this robotic arm. Okay, as per the requirement. So in composite, if the fibers are not oriented as per the design, so that may affect the end performance of your component. So likewise here we have the different kind of the weaving styles of your composite that can be used for the different applications. Say I have the plain view, I have the twill view. So where we have this.
Sorry to interrupt, Dr. Ankush.
Yes, sir.
Last 10 minutes.
Okay.
Okay. Thank you.
So where we can have the different kind of weaving patterns. So we have to be selected what kind of weaving pattern we need to be, or how my fiber will be oriented in order to get the specific properties. Okay. Then we have the different kind of the matrix material. Matrix basically a binder. So in the polymer matrix material, we have the thermoset as well as the thermoplast. So polyester, vinyl ester, epoxies, phenols. Then some of the thermoplast materials are there. PEEK, PEG, then the ABS. These are the thermoplast material that can be used to develop the composite materials. Like in the composite, the role of the fiber and the matrix material is very much important. So the fiber reinforce provide the tensile and compressive strength in the fiber direction, whereas the role of the matrix material is to bind and stabilize the fiber, provide the load transfer, carry the load perpendicular to the fiber direction, and it has the influence by the service temperature, chemical, and all these things. So this is like how. So basically, in the polymer matrix composite, now you can see that my one constituent is your fiber and second is your polymer. Polymer is more temperature sensitive, but if we'll combine both together, then yeah, aggregate property we can achieve whatever for whatever application we need to be defined. Okay. So this is about the common manufacturing process, how you just manufacture the composite process. These are the different manufacturing processes. See, this process need to be understand. Why? Because like these are the area where the industry 4.0 is applicable. So say for example, this is your filament winding process. So filament winding process already it is, I can say it is a continuous process. So you need to be only do the programming. You need to do you need to after like you once you have the layup sequence, you have decided the angle, then only you need to do the programming, and this programming can be input of your machine, and after that automatically fiber placement will be takes place. Okay, so how this industry 4.0 has been implemented in this system? Yeah, again, you can do the online inspection. Yet this online inspection is not implemented. So say for example, I have defined कि आपका say for example at 25-degree my fiber angle should be oriented in a single layer. While the second layer my angle should be say for example 30-degree. In some cases it might be possible my fiber angle is not proper. So online inspection immediately can give the comment to your this arm that fiber angle is not proper, so it will be stopped immediately, and then one worker can come and he can do the proper arrangement in order to be achieve those kind of the angle. Then this is your pultrusion machine. So again it is a continuous process where the less human intervention is there. So once you set up the process, it will be continuously move. Okay. And here also as a industry 4.0, the online inspection can be adopted so that you can reduce the waste, you can minimize the waste, you can improve the efficiency and the productivity of your component, and this will be vacuum infusion process. So when we have the next session, and that I'm going to be tell you about how this industry 4.0 can be implemented in this kind of the processes in order to be achieve the good product quality. So this is just a small video of spray process. I'll just show you. So how this, so this is continuous fiber. It is a gun. So where my this fiber will be chopped, and simultaneously my resin system will become, and the final composite layer will is possible. So I'll just tell you, yeah, see. So the fibers are there, and then parallel resin is also coming. So it will be cured. So this is one process of spray process. Then second, it is a filament winding process. You can see here. So I'm talking about this angles. So again, so this kind of the process widely used to making the pipes and pressure vessel. This is your pultrusion process. So this pultrusion process is used to make the different profiles like this. So here how this industry 4.0 can be implemented exactly point wise I can or will discuss. Then this is the next vacuum infusion process. So complete your wind turbine blade or the big yacht is being manufacturing using this process. So where the infusion will be takes place by the help of vacuum, and the entire system can be made through this. Like so, these are some examples. So this is a wind turbine blade. How this will be, and this industry 4.0, the integration of the sensors and all these things very much important for making this big part size. Okay, so yes, the time like the already sir has given the signal for the time. So the rest thing maybe we can discuss when we have the next session, maybe on the 25th. So where actually I'll show you that how this your process, basically the manufacturing process has played the role in order to be improve the part quality. Okay, so here we are just have one study where we just make the same component or the same kind of limit without changing the material, but with the two different processes where one is completely with the human hand, second is with the help of the vacuum pressure, and how it affect the mechanical performance of your component. So with that, I think that I'll just stop the talk, and then we can have some time for the maybe discussion or for the question answer session.
Yes,
So
yes.
thank you, sir. Over to you.
Yes, Dr. Ankush Sharma, thank you so much for this very informative lecture. We have some questions from the participant.
Yes, sir.
Just I'm picking from the chat box. It is asked by Devashish Sarkar that implementation of Industry 4.0 in manufacturing in India is still limited. Why?
Yeah, so already like see, there are lots of challenges are there. See, the major big industries adopted this industry 4.0, but the small, I can say SMEs or MSC is still hesitate to implement those kind of system because of the integration of the sensors and all this. And now most of the oil industries having the oil machinery, and again it is not that much cost effective to I can say to upgrade their system. That's why they are not thinking to be adopt this industry 4.0. But yeah, now the new industry, though the person who is establishing the new machinery in their plant, they are coming with the industry 4.0. So I can give an example of say like textile industry. Textile industry is very old and the mature, but still you can see the old industries, they are still hesitate to be change their process. And second is the trained human power. if we are implementing the machinery with the integration of this industry 4.0, then the skilled manpower is required. And still in India, the skilled manpower is challenged. That's why the many industries is not adopting 4.0, industry 4.0.
Yes. Yes, so the next question that is definitely related to the your answer as well.
Yes.
The question asked by Amit Galpade. With the advent of AI-driven technologies in the near future, can we say we will be moving towards Industry 5.0, where human inputs will be minimal?
Yes. So now if we'll talk about the industry 5.0, na? So in industry 5.0, they are more like they are focusing with the human intervention now. So this is now a major difference between the industry 4.0 and industry 5.0. So with this AI driven system, the human intervention is required in order to be take proper decision. So when the human intervention will be there, then we can see it will be with this industry 4.0 with human intervention, we can say it will be a industry 5.0, sir.
Yes. Maybe the last question from the Jani Dhruv Kumar. He's asking that, sir, is there any scope of installation of automated fiber placement setup at Atira?
See, in India, right now, not a single industry is adopting this kind of the AFP process. However, right now we are also not thinking because again, it is a very costly technology and excepting this aerospace industry, no other industry is willing to adopt this automatic fiber placement technology because of the cost. In AFP, now see, you can see, I can give an example. Still, say for example, we are developing so many component using the pre-preg. Okay, but India is still not able to make a carbon fiber of aerospace grade. However, some of the industries like you might have heard about in the news about the Reliance, about the Jindal. So they are putting their effort in order to make the carbon fiber. So carbon fiber development, then convert it into the pre-pack because AFP in the AFP process also it is one kind of the pre-impregnated fabric that need to be layered. So this is again I can say the next level. So still we are struggling with the first level. Once we'll be achieve these things, then we can think on the second level, which is of AFP and all these things. So right now we
Yes.
don't have any
Yes.
plan to establish those technology at our place.
Yes. I can see a few questions more in the chat box. The next question is asked by Rahul Kumar Sen. He's asking that what the actual role of cloud computing in composite material.
So yeah, it is again related to the process thing. So if I talk about the cloud computing, so say for example, every data that can be captured, that can be put on the cloud. So say for example, to do the operation from one station to the second station, all the data will be captured. And say for example, I have just given a good example. So say for example, one design company is there, one manufacturing unit is there. So they are sharing their ideas, their design, their things on the cloud. And by sitting anywhere, they can discuss to each other, they can implement the design, they can do the modification to design, and this design directly put on the machine. So how this cloud computing is taking or playing the role in the composite manufacturing itself.
Yeah. I am seeing here a very important question asked by Dr. Manas Bhuyan. After implementation of Industry 4.0, what is the error probability in the system?
See, if we'll talk about error probability, so see, this Industry 4.0 is the integration of not only the single system by the adopting the single system, we can minimize the look, we can completely remove the error. Yeah, but we can say the error like can be minimized by, say, for example, 100% to the 10% or 20%. So this much probability is there by minimizing the error into the system. Okay, so this is like how industry 4.0 is helped to like reduce the things.
Yes. As I can see, number of questions participants are asking. So I suggest to all participants, definitely you have very good questions. You can contact Dr. Ankush Sharma via email also. And definitely you can start the conversation and future collaboration also. So I would like to thank Dr. Ankush Sharma on behalf of Department of Mathematics, Department of Mechanical Engineering, Pandit Dindayal Energy University for this valuable, informative lecture. Thank you, sir, for accepting our invitations.
Thank you, sir. Thank you.
Thank you, sir, for chairing the session, and thank you, Dr. Ankush Sharma, sir. Before we should actually conclude, I would like to request all the delegates to please actually switch on your video so that we can click on the common photograph.
And also I request Dr. Ankush Sharma, sir, to post his email.
Yes.
Participants are asking about your email.
Yes. So I can see also one question by Dr. Himanshu Patel. How can digital twin technology be utilized to optimize the design, manufacturing, performance of monitoring the composite material? So like I have certain case studies on that. So when we have the session on the 25th of December, at the time I think I'll be elaborating the more better way about this digital twinning in composite sector.
Sure, sir. Sure.
So all the participants, definitely, I request you to switch on your video. It is right time to give your attendance. Okay.
Dharmik, have you taken it?
Yes, sir. It is done, sir.
Okay. Thank you. So now we sincerely thank Dr. Ankush Sharma, sir, for his enlightening talk on Industry 4.0 for composite industry. So thank you once again for accepting our request and actually giving insights related to the Industry 4.0, how it is being used actually in the industry. So I think all of the delegates has been benefited with your talk, sir, and we are eagerly waiting for you on 25th.
Thank you, sir. Thank you to consider me for your FDP, sir. Yeah, thank you.
Sure, sir. Thank you so much. So now I would like to conclude. So on behalf of the organizing committee, I would again like to extend my heartfelt thanks to the Honorable Director General, Sir, Honorable Director, School of Technology, both heads of the Department of Mathematics and Mechanical Engineering, all distinguished speakers, organizing team members, and all the participants for their active participation. So the knowledge that is being shared today, I think, has been truly enriching, and I encourage you to carry out this momentum forward. So tomorrow we have even more exciting sessions lined up that will further deepen your understanding and broaden your perspectives. So I request you all to stay motivated, stay engaged, and we look forward to seeing you all tomorrow at 6 p.m. on the same platform. So thank you once again for attending the sessions on day one. Thank you, all the participants and the speakers.
Yeah, thank you, and good night to all. Thank you. Bye.
Good night. Good night. Thank you so much, sir.
Bye. Good night.
Bye.
Thank you, sir.
बराबर